What's up, y'all? This is your video on chi-squared test of homogeneity. This one and the next one on chi-squared test for independence are going to be very similar because they both deal with two-way tables and you run the tests essentially the same way. All right, so let's jump straight into this. I'm hoping that you already watched the Goodness of Fit video, which had a lot of the chi-squared information in it. We're going to run these tests very, very similarly. A lot of the things that show up in Goodness of Fit tests show up here with just a couple of little differences. So I'm going to tell you a little bit about those differences. If you haven't watched that video, you should go back and watch it because my brother makes an appearance and it's kind of hysterical. So if you need a laugh, go find my brother in the Goodness of Fit video. Okay, so chi-squared test of homogeneity. Very, very fancy term for how does changing one category affect another category, right? So say, for example, you were looking at like restaurants. Say it's like a chain of restaurants and there's 3 or 4 different locations of that chain restaurant. And you wanted to see how did going to like 4 different restaurants of the same chain, like how did that affect the taste or the flavor of like 3 or 4 different recipes or something that they cook there. Okay, so we do chi-squared tests of homogeneity essentially when you want to compare how changing one categorical variable affects another. So you're going to see data show up in a two-way table. Okay, the Goodness of Fit ones were just a one-way table. Okay, the homogeneity and independence tests are almost exactly the same. It's just different in how their samples are taken and then how you write the hypotheses. So for homogeneity, you have to take independent samples from each population. Okay, so you can't just like take one big sample from the whole population. You have to take like a sample from this group, a sample from this group, a sample from this group. So that has to be done separately, like before you run the test, or it has to be subjects randomly assigned to different treatment groups. So like in an experiment, okay? The difference between homogeneity and independence is really similar to the difference between doing like a cluster sample. If you remember those way back from Unit 1, a cluster sample and like a stratified sample, okay? So the great thing about chi-squared tests is that the hypotheses are really easy to write and it's pretty much the same no matter what. So for these tests, your null hypothesis is that there is no difference. So you'd say no difference in the distribution of categorical variable 1 and categorical variable 2. Okay, so no difference. Okay, and then your alternate hypothesis is that there is a difference. In the distribution of categorical variable 1 and categorical variable 2. The conditions are exactly the same as Goodness of Fit, so still simple random sample or random experiment. 10% condition, where you do 10 times the sample size, is less than the total population. And then large counts is expected values have to all be greater than 5. But you do calculate the expected values a little bit differently. Okay. Another thing that's a little bit different is the formula for degrees of freedom. Because you have 2 different categorical variables, you have to include them both in the degrees of freedom. So the way you calculate degrees of freedom, it's still something minus 1. So number of rows minus 1. And then you have to multiply that by the number of columns minus 1. Okay, so in the example that you see down here, let me switch that back. So in this table right here, see there's 3 rows, 1, 2, 3, and 3 columns. So this would be 2 times 2. So the degrees of freedom for this table right here would be 4. Okay. All right. And then it's also a little bit different in the way that you calculate your expected value. Because again, you have like two different variables and you have rows and columns that you have to deal with. Okay. So the formula for your expected counts is the row total times the column total divided by the table total. Okay, which you can see in an example right here, which you also have on the right side of your screen, but I think it's a little easier to see. It's a little bit more blown up on the left. So if you wanted to find the expected value for this box right here, the French and no music. So French entree, no music. Okay, the row total is the total for French, which is 99. The column total is down here, 84. And then the table total is 243. So the expected value here is 99 times 84 divided by 243. And just like you had to calculate all of the expected values when you did goodness of fit tests, you also have to calculate the expected values here for homogeneity and independence tests. I know that's going to take a lot longer because there's a lot more data, but never fear, just like the goodness of fit test, the calculator is going to do almost all of this work for you. Like you don't have to calculate all the expected values. The calculator will do it for you, okay? Couple other things when it comes to homogeneity tests. P-value still comes from the calculator. So if you were going to do all of this by hand, I would say then at the end use chi-squared CDF, but I'm going to show you the calculator is going to do the whole test for you. So just like we use chi-squared GOF, we're going to use a different chi-squared test on the calculator for these, okay? Here in the notes is your calculator path when you're doing a homogeneity or an independence test. For these, you don't enter everything into a list, okay? Like we did with the goodness of fit ones. Remember, you had like the two columns. You had your observed values and then you had your expected values that you entered. We're not going to do that here. For these tests, you actually want to use a matrix. And then I'm going to show you how to do that on the calculator in a second. And then one other thing I want to make sure that you know, which we talked about briefly in the last video, is with chi-squared tests, a lot of the times you do want to do a follow-up analysis because you have so much data and so many categories. Like in this one, in this table that we have here, with the entree type and like the music type, it's only two categorical variables, each with three like subcategories or choices, and you end up with 9 different things. So it doesn't really help you to know that like, okay, the distribution is different than we thought it was. What's really the most helpful is to know what specific combinations are the most different than what I would expect them to be. Like what's contributing the most to the chi-squared value. Okay, so if you go and reject the null, you may be asked to do a follow-up analysis. Okay, so you want to see which of those cells contribute the most to the chi-squared value. And I'm going to show you, just like we did on the last one, where those values are on the calculator. The way that you would say that is you would say the largest contributors to the chi-squared statistic are, and then you would list what those combinations were. So maybe it was French music and a French entree, or an other entree with no music or something like that, right? And then you would say that there are more or less of those individual combinations than we would expect, Okay, so give me a second to clear my screen. I would advise, if you haven't done so already, go ahead and open your calculator and just pull up a blank like calculator page. You don't have to add a list or anything like that, just a blank page. So we're going to enter some data in a matrix, and I'm going to show you how to do these homogeneity tests. All right, so see you in just a second. Okay, everybody, so here is your chi-squared test of homogeneity example. So in this problem, they are talking about the distribution of a survey that was given. So essentially, they're trying to figure out, and if you look at the question, you can see that. It says, do the data provide convincing evidence of a difference in the distribution of opinions about how high schools are doing among Black, Hispanic, and white parents? So we're trying to figure out, a bunch of parents were given this survey and they were asked, how are the high schools in your state doing, basically? Excellent, good, fair, poor, or you don't know enough to say. So we want to see if, basically, if there's a difference in the distribution among these three ethnicities and races, right? Does changing the, and you can't obviously change the race of a person, right? But like, does changing the race of the person you select, does that change how they feel about how the high schools are doing? Okay, so that's how I know that this is a homogeneity test, because we're trying to see how changing one categorical variable, so in this case, the race of the parent, how does that change the other categorical variable, which here is the school rating, how they would rate the school. Okay, so I want you to focus for the first part of this on the left side of the screen, because I'm not going to write the whole thing out here. But you, just like with the goodness of fit test, you can skip the parameter because the parameter shows up right in the hypotheses. Okay, so your hypotheses, your null hypothesis, is always that there is no difference. Remember, so the question is, do the data provide evidence of a difference? So our status quo is no, there is no difference, and we have to prove otherwise. So my null here is there is no difference in the distribution of opinions about how schools are doing. So that's one categorical variable for, and here's the other categorical variable, Black, Hispanic, and white parents. And then my alternate hypothesis is there is a difference. That's what we are trying to show in the distribution of opinions about how schools are doing, one variable, for two, the other variable, Black, Hispanic, and white parents. Okay. Assumptions. You're still checking your three assumptions. Okay. It said in the problem that this was a telephone interview with three randomly selected groups of parents. Okay. And then, so that's your random sample. For the 10% condition, I did 10 times the total for each of the races. So you don't have to do it for both categorical variables. You just have to do it for one. And the race one is what I actually care about. Like, I don't really care if there's more than 680 people, so 68 times 10, that would have rated the schools excellent. I don't really care about that. I care more about like the individual people, and like what we're actually changing. So it's reasonable to assume that there's more than 2020 Black, 2020 Hispanic, and 2010 white parents in this big school district, okay, or in the state. And then for large counts, I know you haven't actually calculated expected values yet. Just say all expected values are greater than 5, okay? So next, this is a chi-squared test of homogeneity. And then we're going to set our alpha value at 0.05. So the way that you would write that is you would say chi-squared of homogeneity. You can say just like homogen if you want, but I'm going to write the whole thing out. Homogeneity. We're going to set our alpha value at 0.05. Okay, so here's where the craziness comes in, is calculating the test statistic, okay? because normally you would have to calculate each expected value. That's what we did for goodness of fit. Calculate each expected value by hand and then plug all of that in. No. Stop right there, okay? Once you've gotten to this step, the name the test step, stop and enter everything into your calculator in a matrix and store it as a variable, okay? So I'm going to show you how to do that. So I'm going over to my calculator. I got to move this. So here I am in my calculator. I'm just on a regular blank calculator page. So the very first thing you have to do, these are not lists. You want to enter these as matrices. So press the menu button, look for the menu that says matrix and vector, and then you want to go to create, and you're creating a matrix. And then it's going to ask you how many rows, how many columns. So let me go back to my data here. My data has 5 rows and 3 columns. So I'm going to say 5 rows and 3 columns, and I'm going to say okay. And there's my matrix. So I need to go ahead and enter that data. Okay, so give me just a second. Pause your video along with me here. Enter the data into the matrix. Okay, I will see you momentarily. Okay, so I went ahead and entered all of the values into my calculator into this matrix. So here's my matrix. Next thing is you want to store it as a variable so that way it's easier to run stuff on it, like run the actual chi-squared test on it, and it's easier to access later. So make sure that your blinker is out here, so it's not inside the matrix. You want it out here, okay? And then here's what you need to press. You need to press Control and then the var button, and that's going to give you a little arrow, and then you just want to name it something, right? So you have all these keys down at the bottom. If you're on the simulator like I am, you can actually type it. So this was it's like a school survey, right? So I'm just going to call it school, and then I'm going to say enter. So every time I type the word school in here, that's the variable, and it will show me my matrix, okay? So once you have this, you need to actually, we're gonna dispense with all the craziness, and we're just gonna run a chi-squared test, and it's gonna give us all of our lovely expected values. It's gonna give us the chi-squared value. It's gonna give us the p-value. It's gonna give us everything. So here's how you access that. Press the menu button, go down to statistics, and then you want stat tests. And this one is a two-way test. Your calculator is not going to distinguish between homogeneity and independence. Because remember, I told you they run exactly the same. They just are different in the way that their hypotheses are phrased. Okay, so two-way test. And then it says observed matrix. So that observed matrix is this. Right? That matrix that you just ran, because those were the actual values that came from the survey. You're going to press OK, and there's your whole thing. Okay, so you have your chi-squared value, your p-value. It shows you your degrees of freedom, but I'm going to show you how to calculate that. I'm going to do that in a second. And then you have this that says EXP matrix and comp matrix. So I'm going to go back to both of those in just a second. I need to make sure that I write down what my degrees of freedom are. So I'm going to do that really quickly. So remember, degrees of freedom is the number of rows minus 1. So number of rows, there's 5 rows. So 5 minus 1 times, and then the number of columns is 3 minus 1. So this is 4 times 2. Which is 8, which is exactly what showed up right here for degrees of freedom, okay? Then, hopefully this COMP matrix looks familiar because it's the component part. Sorry, my brother just came in. 1 second, pausing. See you in a sec. All right, howdy everybody. Sorry about that. Had to go and help my brother out with something. So we just did degrees of freedom, and then I'm pretty sure I was about to show you how to access your expected values in your matrix. So let's go back to the calculator. Okay, so if you remember from the goodness of fit tests, the COMP is the components that make up the chi-squared value. So the individual values that are added together to make this number, the 22.4261. This, the EXP matrix, is your expected value matrix, right? So you don't have to calculate the expected values. This test, by running this test, it will do that whole thing for you. So if you go and press the var button, VAR, see this? It says stat.exp matrix. Okay, if you click on that and press enter, there are all of your expected values, which I have already filled in right here. You do have to list all of these if you're going to do a problem like this. Obviously, it's not on the AP test this year, but it's good practice just in general to show that you've met all of your conditions. So you would go through and write all of these out. I'm obviously not going to write them all out because I've typed them for you here. But if you were going to do this problem, you would fill all of those expected values in. Okay. So then once you have your expected values, you can actually write out what the chi-squared statistic is. Okay. So just like the goodness of fit test, you only have to do one. Just write one example of how you calculate it and then write the number that was given to you by the calculator. So remember, chi-squared is observed minus expected squared over expected. So I'm going to do the top left corner. So the Black parents who rated the schools excellent. So the observed value was 12 minus the expected value was 22.7. So I'm going to do that and square that and then divided by 22.7. So that's only one component of your chi-squared statistic. If you were going to write this all out by hand, you would have to do this one, then this one, then this one, this one, this one, this one, right? It would take you forever. So just do one and then say plus and say ... and then say equals and then write out the value that you get from the calculator. So on the calculator, if I scroll up a little bit, back to this two-way test right here, the chi-squared value was 22.4261. So that's what I'm going to write. 22.4261. So that is my chi-squared value. Okay, then the last of it, really easy, what you're used to doing. Okay, so p-value here, remember the way we write these, it's the probability that chi-squared is greater than, remember it's always going to be greater than because these are skewed to the right. All of your chi-squared distributions are skewed to the right and they always are greater than 0. So you want to use greater than here as your cutoff point. And then you're using your chi-squared value that you got from the calculator. So chi-squared, probability that I get a chi-squared value this extreme, so this big, 42.4261, right? Or larger equals, and then again, you get this p-value directly from the calculator. So it's this, the thing that says p-val, very easily and nicely labeled for you. So 0.004185, 0.004185. Now you can round this if you want. You don't have to write the whole thing out. Like you could have rounded it right here up to 0.0042. That would have been fine. Okay. And then that's obviously less than any alpha value we could have set. Ours was 0.05, definitely less than 0.05. So because of that, we're going to reject the null. Okay. So reject HO. Okay, and then you have your conclusion and context, which again, I'm not going to write out because I have it for you on the left side of the screen. So because p-value is less than alpha, we reject the null and say there is evidence. And then, like I said, I think in the last video, I forgot to write there is enough evidence for HA or to support HA, which states that there is a difference in the opinions about how the school is doing among Black, Hispanic, and white parents. So you can just go straight back to your hypothesis, right? Because that's where you put your parameters. So just take your hypothesis and stick it right there at the end, okay? And then we want to look at if you are asked to do a follow-up analysis, which just in general, if you ever run a chi-squared test, is a good idea to do just because it gives you more information about what really is different in the data than what you expected. So the way that you access that is the comp matrix, which I have filled in right here, but I'll show you how to do it on the calculator. So I'm going to scroll back down, and this time I'm going to press the variable button, and I'm going to press stat.comp matrix. So I'm going to click on that. And these, like I said, are the components of the chi-squared value. So if you add this, all of these numbers together, you'll get 22 point whatever the decimal value was. So it looks like you have the most contribution up here. So these two values, and then I would say probably these two values right here, and then maybe these two values at the bottom. So you would list what those combinations are. So I said the following groups contribute the most to the chi-square statistic. I listed 6 of them. You obviously do not have to list that many. Like 2 is fine, 2 or 3. So if you were to list the things that contributed the most, it would be the Black parents who rated the schools excellent, the Hispanic parents who rated the schools excellent, and then the next largest one was this one, the Hispanic parents who rated the schools good. All right, y'all. So here is one more example for you of a chi-squared test of homogeneity. So if you are following along with me on your notes, I've filled in some extra data. So I've filled in the totals here, and I've also already run this chi-squared test on my calculator. So I went ahead and filled in the expected values table there, but yours won't be filled in. So you obviously will be able to fill those in here as we go throughout this problem. Okay, so in this problem, we're talking about political leanings from a cell phone only cold call sample and a landline only cold call sample. So what they're trying to figure out is, do these data provide convincing evidence at the 5% significance level that the distribution of party affiliation differs in the cell only, like cell phone only and landline only populations? Okay, so remember with these chi-squared tests, because of the way that the hypotheses are written, you don't really have to state your parameters because it's going to show up in your hypotheses. Okay, so the way that I would write my null hypothesis here would be that there is no difference. So there is no difference there's no difference between sorry, that looks crazy. Hold on. So there's no difference between, and then my two categorical variables here are party affiliation and phone type. Okay, and then my alternative hypothesis is that there is a difference. So there is a difference between ... right? I'm not going to write the whole thing out, but you would just repeat party affiliation and phone type. Okay, next is assumptions. Okay, so randomness, they did tell us that it was a random digit dialing telephone. So you would just say stated in problem. Okay, for my 10% condition, my sample size here was 200. So this, I would do 200 times 10, right? So remember, 10 times the sample size, so that's 2,000. That's definitely less than the total number of under 30 people, and then I'm pretty sure this is in the US. Okay, and then lastly, for your success fail slash, remember it's also called large counts, you would just say all expected values are greater than 5. Okay, even though we haven't calculated them yet, like you haven't calculated them yet, just say that they're all greater than 5, because 99.9% of the time they are going to be greater than 5. Okay, all right, and then for my test here, this is, obviously I told you at the start, this is a chi-squared homogeneity test. Okay, which you can tell, one, because it's data coming from a two-way table that we're comparing two categories. Okay, but the other way that you can tell is based on how the hypotheses are written. Okay, and here we're trying to compare and figure out, does changing the cell phone type affect in some way the party affiliation. Okay, and obviously another way you can tell here is because of the way that this was done. This is a survey, and they took data from two individual samples, right? So they did like a cell phone only sample and a landline sample, right? So we took samples from each population, right? And then categorized within those individual samples, okay? So those are a couple of ways you can tell that this is a homogeneity test rather than an independence test, okay? All right, so let's scroll down a little bit, okay? Now, once you get to this point, okay, remember, stop what you're doing and plug your information into your calculator. Remember, with these two-way tables, you're not plugging it into a list, you are plugging it into a matrix. Okay, so make sure that you plug just these values, so not all the totals, just these values into a matrix in your calculator, okay, which I have already done, okay? And then after that, once you have that matrix in, go ahead and calculate your degrees of freedom, okay? Which here, remember, degrees of freedom is the number of rows minus 1. So there's 3 rows, so 3 minus 1, times the number of columns minus 1, right? So this becomes 2 times 1, which is 2. Okay, once you have your degrees of freedom and your observed values in a matrix, go ahead and run just a chi-squared test on it, okay, in your calculator, all right? Because that's going to help you with that'll help you write out what your expected values are, which I already have pre-done for you here, but you should make sure that you write all of those out, okay? And it will also give you your test statistic, your chi-squared value, and it will give you your p-value, okay? So once you run the chi-squared test in your calculator, okay, what you do next, okay, is just show one example of how you calculated an expected value. So remember, expected value is the row total. So let's say I'm going to do this example. Right, so Democrat leaning, cell phone only. Okay, so my expected value is always the row total, which is 96, times the column total, which is also 96 in this case, divided by the table total, which is 200. And that gave me the 46.08. Okay, so just show them one example, and then after that, move on. Okay. What comes next is your chi-squared value. So remember, just show one example of how it was calculated. Okay, so it's always observed minus expected squared. Okay, so my observed value for Democrat leaning with only cell phone only. So that observed value was 49. So 49 minus the expected value, 46.08. And then I'm going to square that. Okay, then divide that by the expected value. So again, 46.08. Say plus, then dot, dot, dot. Whoop. And then say equals, and then literally just say exactly what your calculator gave you. So my calculator gave me for my chi-squared value 3.220 if I round. Okay, so that's my test statistic. All right, remember O stands for obtain my p-value, so that's the probability that chi-squared is greater than 3.22. And then remember, your calculator is going to give you that information as well. So when I did that in my calculator, I got 0.1999, which is greater than any reasonable alpha value, right? But they told us that alpha was 0.05. Okay, so based on that, because my p-value is greater than alpha, I'm going to fail to reject the null. All right, and then my very last thing that I have to do here is state my conclusion in context. Okay, so I'm actually going to go ahead and type this. Okay, so you would say because the p-value is greater than alpha, we fail to reject the null hypothesis. We would say we don't have enough evidence to say that there is a difference between party affiliation and phone type. Okay. All right, so that is your entire chi-squared test for homogeneity. Okay. As always, let me know if you have questions, and I'll see you in the next video. Bye, everybody.